In our universe, when you change from a non-moving perspective to a moving one, or vice versa, that change of perspective is represented by what's called a Lorentz transformation, which is a kind of squeeze-stretch rotation of spacetime that I've mechanically implemented with this spacetime globe. The spacetime globe illustrates many of the features of special relativity, like length contraction and time dilation, and the twins paradox, which is a linguistically confusing situation that can arise in special relativity when somebody learns about time dilation. The fact that in our universe, things moving relative to each other each view the other's time as passing more slowly. As the paradox goes, if each person views time as passing more slowly for the other, then who ages more? If my twin travels away from Earth for a while and then comes back, who's actually younger when we meet again? In general, when you have a confusing situation in relativity, it's really helpful to actually draw or use a spacetime diagram to understand what's going on. We'll use the spacetime globe. The situation is this. You're sitting on Earth for, let's say, 12 seconds. Your twin travels out at a third the speed of light for what you measure to be 6 seconds, and then they turn around and come back at a third the speed of light for what you again measure to be 6 seconds. So what does your twin think? Well, to understand the situation from their moving perspective, we need to transform the spacetime diagram so that they no longer appear to be moving. That is, so that their world line is vertical, which is what it means for the spacetime diagram to represent their perspective. Having done so for the outward leg of the journey, it's clear that your twin would say that leg of their journey took them about 5 2/3 seconds. And then they turned around and headed back to Earth, which corresponds to a different moving perspective. Let's transform things to see how they look from that perspective. That is, so that the world line of that leg of the journey is vertical. Having done so, it's clear that your twin would say that the return leg of their journey took them, again, it looks like about 5 2/3 seconds. So from the perspective of your twin, their whole journey takes 5.66 plus 5.66 equals 11.3 seconds, while for you it took 12 seconds. So you, who stayed put, are older. The key to why the two of you do in fact age differently is that your traveling twin has two separate perspectives during their journey, and they accelerate between them, while you, staying put, only have one. And that's the resolution to the linguistically confusing twins situation, demonstrated with a hands-on spacetime diagram. I want to say that even though I know and understand the math and physics behind this, my belief in the trueness of the solution to the twins paradox went up 1,000,000 times the first time I actually measured the proper time of each twin in real life, like with my hands on the spacetime globe. So I hope I've managed to capture even a small percentage of that gut-level feeling in this video. You also don't have to use Lorentz transformations to figure out the solution to the twins paradox if you know about proper time, because proper time is a way of calculating the time that passes for somebody according to their perspective. So in the case of your twin, on each leg of their journey, they take 6 seconds to travel the distance light would travel in 2 seconds, or 2 light seconds. And taking the square root of the difference of these numbers squared gives a proper time of 5.66 seconds for each leg of their journey, which is exactly what we measured on the spacetime globe. If you're interested in a little more insight into how each person can view time as passing more slowly for the other and how that makes sense, and I promise it does, I have another pair of videos diving into more detail on the twins paradox that I highly recommend you check out. And to deepen your personal understanding of the resolution to the twins paradox, I highly recommend Brilliant.org's course on special relativity. There you can work through the calculations I've glossed over in a step-by-step guided exploration, giving you essential hands-on experience with spacetime intervals and other tools of relativity along the way. The special relativity questions on Brilliant.org are specifically designed to help you go deeper on the topics I'm covering in this series, and you can get 20% off of a Brilliant subscription by going to brilliant.org/minutephysics. Again, that's brilliant.org/minutephysics, which gets you 20% off premium access to all of Brilliant's courses and puzzles, and lets Brilliant know you came from here.